I'm Phương Cao. Today I'm presenting our system CAUDIT, a new approach for continuous auditing of SSH server to mitigate from brute force attack. This is a joint work and it has been deployed in production at the National Center for Supercomputing Application at University of Illinois. First, let me give you a brief overview of the network in which we have deployed CAUDIT. NCSA hosts a Blue Water supercomputer in which there are thousands of workstations and more than 28,000 of computing nodes. So Blue Water is a petascale supercomputer, is connected to the NSF International Research Network as well as the public internet. Now, with such enormous computing power and collaboration from industry partners, NCSA has enabled critical research in a variety of areas such as genomics, astrophysics, and earth sciences. Now, the unique things about the NCSA network is its openness, in which the collaborators around the world can connect to the NCSA network remotely via the internet, and so as the attackers. We have seen many types of attacks targeting NCSA, but the most frequent type are the SSH brute force attack, in which the attacker used the availability of stolen key as well as the leaked password and try that on the NCSA infrastructure. Now, to protect the NCSA infrastructure from such attack, we have contributed to the open source security monitor, such as the BroIDS and also OS Query, and use the information from those monitors to detect the attack. Now, the problem here is that such attack could come in a very large volume. We usually see the attacks in the order of 10 millions of attack attempts every day, and that creates the overload in both the alert system and also overload the security analyst and make the security system does not work as expected. All right, so the problems here is how to audit internal host against the SSH brute force attack. And there are three main challenges of this problem. First, as I mentioned, is the high volume of the attack that overloads security monitors. The second challenge is that it is difficult to enforce the password policies on individual devices in the network. And finally, we don't have a good understanding of such attack at a large scale in the internet scale. Now let me put this problem in perspective and justify why is that important. As I mentioned, many of the stolen credentials are available and also many vulnerability in OpenSSH server and other kind of libSSH is still available. In the last year, we have an authentication bypass vulnerability in the libSSH. And if you look around in the recent data breaches, the main cause of those breaches is failing to password protect the SSH server. And in some cases, the server are exposed to the internet for the attacker, so they don't even have to exploit any vulnerability. And as a result, some companies have to pay millions of dollars for settlement as a result of the data breach. Now the question is, how other people are addressing this problem? At the academic side and the industry side, we have recent work from Microsoft and LinkedIn, which has been looking at the statistical approach to detect the attack in the similar manner. However, this approach has only been tested on their own system, for example, Azure Active Directory, and they have not been tested on SSH as well as for auditing SSH account. We also have seen the effort from government agency. For example, NIST has published a list of policies to manage the security of SSH keys, but it is still in the responsibility of individual companies to implement and to audit those policies. Indeed, many of the challenges in managing SSH keys are still an open problem, as published by the inventor of SSH in this white paper. To address the above challenges, we have built and deployed a continuous auditing system named CAUDIT at NCSA. The key idea is to use a honeypot to attract external attacks and record them into an SSH database, and then we replay those attacks against the internal infrastructure. So in such a way, we are mimicking the real attack techniques on the internal server without exposing them into the internet. And then the most frequent attackers are fed back into a black hole router so that they can be blocked right at the network border. Now, the trick of our honeypot is that it has been deployed on a /16 IP address space, which mimic 65,000 hosts, a large amount of server farm. And as a result, we have collected more than 400 million of the attack attempts, which is the largest database to date from 76% of the autonomous system in the internet. Finally, all of such attack attempts are currently being shared with our partner, with 9 in the US and 1 in the international, in order to prevent such attack before they evolve into security incidents. As a result, we have been able to protect the internal security monitor as NCSA, making them less impacted by the SSH brute force attack. And because the NCSA network is well protected, we observe a decreasing trend of security incidents year over year at NCSA, which is in contrast of the more data breaches that you observe in the news. All right. So for the talk today, I will first review some of the important internet scale measurements that we observed from our dataset of more than 400 million of attack attempts. And then I will show the key enabling techniques that allow us to deploy and collect such dataset. Finally, I will show some of the benefits of CAUDIT in production. Now, the first question one may ask is that, where are the attacks coming from? Here, we clearly see a power law distribution in which very few ISPs are the conduit for 1/4 of the attacks. In addition, we also see some of the cloud and VPN provider as a conduit of the attacks. Now, let's look at what kind of devices are the conduit of the attack. To give you a little bit of the context, when an SSH connection is made, the client would send a string to identify the SSH client library to the server. And using this information, we can characterize the behavior and the device of the attacker. Now, surprisingly, 47% of the attacks that we found coming from a very outdated SSH library released in 9 years ago. So this library can be found in old IoT devices, which typically lack of auto-update mechanisms. Another observation is that attacks come from libSSH, which recently has a vulnerability, allow attacker to exploit them and potentially use them to drive those attacks. Now, this raised a future research concern about building the shield to protect the IoT devices from being exploited in such attacks, as shown in this paper in Hotnet 2015. So that is a device that attacker used to attack the system, and we also look at the kind of password that attacker used in conducting the attack. Now, the traditional approach of the attacker is to use dictionary-based password, for example, let me in, or using the default password in the management portal of the device, for example, admin, and we see nearly a million of such attempts every day. However, recently there has been a published database of leaked password collected by the site Have-I-Been-Pwned, and they have more than 5 billion of the leaked password collected. By correlating our data and the leaked password from Have-I-Been-Pwned, we observe that the leaked passwords are 3 times more frequent than the default or dictionary-based password. And the use of leaked password could indicate the targeted attack, which is more sophisticated than the brute force attack. Although passwords are typically used for human-to-machine authentication, key can be also used for machine-to-machine authentication in the automated management of cloud servers. We have seen new and unknown SSH keys used in our dataset, showing the fingerprint of the top 5 keys here. It means that those keys could have been obtained from an underground database or undisclosed data breaches, and then used to target our honeypot. The discovery of those keys has led to the adoption of new security policies at NCSA. For example, enforce the passphrase of the key so that in the case of a data breach, the keys couldn't be used without a correct passphrase. The second is to hash addresses of the recent host in the known host file, so that when an attacker has compromised one host, the attacker does not know what other host can be used to perform lateral movement. So those are the important measurements from our dataset. Now, let me show you the key enabling techniques that allow us to collect such a large amount of dataset in operation. Now, the traditional way of setting up a honeypot is to create a new virtual machine with a really weak password and then expose it to the internet and wait for the attacker. Now, doing this, you probably get a few hundreds of attempts a day, and each attempt would be provided with a dedicated shell that allows the attacker to interact with the system and to run code. We have tried this in the past, and although it allows us to observe the attacker behavior, the problems are the follows. First, it is resource intensive and only attract a small amount of attack data due to the exposure of a single IP address in the virtual machine. Second, to properly set up the firewall and permission has to be correctly set up to isolate such honeypot. And because NCSA network is a sophisticated, constantly evolving, to maintain such correct permission in isolation is very challenging. So that's why we have been taking a look at an alternative approach, which is non-interactive honeypot. So a non-interactive honeypot only records the connection metadata of the SSH attempt, which contain some of the key information, for example, the source IP, the client library, and the credential in the form of key fingerprint or the password. And each of the SSH connection attempt here going to the IP space of the honeypot is recorded into a database. Now, the unique technique here to attract the attack traffic is to deploy that on the entire /16 IP space that mimic a large server farm. In addition, the honeypot that we implement, the server key fingerprint is randomized so that the attackers have an impression that they are trying to attack real server with a fresh key fingerprint every time. Most importantly, the servers are non-interactive and reject the attack attempts by default. So they are very lightweight and there's minimal risk in the operation. So the attacker would never be successful getting into an NCSA network through the non-interactive honeypot in our implementation. And all of that result in a large data set of 405 million of attack attempts for us to study. Now you may want to question, how do we leverage such database to further secure the system? Now the answer is here is to do continuous auditing driven by the attacker attempts. The traditional way of auditing is very disruptive to production network. For example, to identify the weak server in such a large network, the strawman approach would be to scan all the networks multiplied with 28,000 nodes, thousands of workstations, and multiplied with 65,000 ports, which is very disruptive. Now, the optimization in our audit is two things. First, the audit here is driven by the existing network monitors. For example, we discover the available SSH host in our network by subscribing to the alert feed in the Bro IDS to identify the port the machine based on the SSH handshake activity in the network. And second, our audit is driven by the new type of attack attempts, for example, new password or new key that attacker put on our honeypot and prioritize over the new and unseen password. And because of those optimizations, our approach is less disruptive to the operational network. And because it uses all the standard monitoring tools, it can be seamlessly integrated into existing network infrastructure. Finally, the resulting malicious host and the malicious IP from the honeypot and the auditor are fed back into a black hole router deployed at the network router. Now, the goal of the black hole router is not to block all the traffic because that would result in lots of false positives. We only aim to block the most aggressive attacker so that we can protect the internal security monitors from being overloaded. So that is a key techniques that I have shown, and you can read more about that in the paper. Finally, let me tell you a little bit about the experience, the benefits of the CAUDIT in the operational network at NCSA. Now, the deployment of the black hole router at the border has really has blocked more than 57 million of the connection attempts on a daily basis. And to further show the benefits of the black hole router, you can look at the chart here, which show the number of recorded attack attempts on the period when the black hole router is operational. The mean number of attack attempts is 65,000 of attempts per day. But when the black hole router is maintained, then all the attacks can make it to the honeypot. And we've seen up to 21 million of the attack attempt per day. That is a 300x difference in the number of attack attempts. And that really shows the benefits of the black hole router at the network border to stop the attacks. And the result of the continuous auditing is that it has preempted potential security incidents in which it has found one of the smart devices that repeatedly scanned the network for 700 times before being stopped. And it also found several of the weak hosts and one unsecure device that store the HPC research data. In the future, we plan to extend our honeypot so that it can be used to attract other kind of attack other than SSH brute force attack. And also, we want to evaluate the effectiveness of the alert sharing network in the detection and preemption of large-scale coordinated attacks based on the SSH brute force attack. In conclusion, in this paper, we have shown that SSH brute force attack can have significant impact on the network security monitors and network security operator. However, the existing solutions do not work with a large-scale system. And our approach has the four main components in which we have a honeypot that reveals the use of private key and the leaked password in the attack attempts, the continuous auditing that have preempted several attacks from evolving into a full security incident. Our black hole router at the network border successfully blocked 57 million of the attack attempts on a daily basis. And our data is being shared with the partner in the alert sharing network. Finally, our approach is open source. It is compatible with standard tool and ready to deploy at this URL. So please go and check it out. Thank you.
Okay, I guess you're standing between us and lunch, but I'll ask you a question anyway. Sure. So you showed something on slide 8, which is interesting, that the number of attacks to NCSA was decreasing.
Yes.
And your speculation was this was because NCSA somehow became more secure.
Right.
There's an alternative theory that maybe NCSA is not an interesting target for attackers. That attackers find things which they can monetize and make money off. So why do you think this is actually going down? Like, what's interesting at NCSA for an attacker to go look at?
So the interesting thing is two things. First is the computational resources of the supercomputer, and you can do lots of things with supercomputer. For example, you can use that to run mining, for example, and we have not seen that. The other thing is the kind of critical data that it is hosting. For example, the patient data in collaboration with the Mayo Clinic, and those could be the valuable targets for the attacker. And we have seen increasing attack attempts, but less of the successful incidents because of the use of CAUDIT with other security monitoring tool at NCSA.
Any other questions? No? We can thank the speaker once more. Thank you.
Thank you.